Dimitrios, are you taking over?
Thanks a lot, Claudio. Thanks a lot, Marco.
Thank you.
So our next speaker is Oliver Stasse. Oliver, you can try to share if you're there. Yeah. Hi. Oliver is from the Geppetto team of LAAS-CNRS in Toulouse, in France. He's going to talk about memory of motion as part of the work that they're doing on TALOS robot from PAL Robotics of the EU Memmo project. Oliver, whenever you're ready, off you go.
Thank you very much, Dimitrios. I would like to thank the organizer to invite me to such a great workshop. Very nice speakers. So it's always interesting to see the works. So what I will present you is some works we have been doing in the team that I had the chance to lead since 1st of January of this year. And you'll see that I will be talking about a lot about the big guys on the left, the TALOS robot built by PAL Robotics based on our specification. So in the ERC grant of one of our colleagues, Jean-Paul Lemont, we had to specify humanoid robots. So this is what we did based on the experience that we had on HRP2, the humanoid robot on my right. And the only company who take the guts to try to build this robot was PAL Robotics, and I'll try to show you the advantage and disadvantage of what we run. And I think there will be another talk later on after Oak Expert, which will be from PAL Robotics with a new humanoid robot, and I think it's going to be interesting. So the application field that we have is as we are in Toulouse, and we have the headquarters of Airbus. We have a joint lab with the aerospace industry. And I would like to give you a glimpse of what is the impact of the tools that we are developing in legged robotics, which go beyond the quadrupeds. I think the quadrupeds robotics is now booming, and I think it's super nice. But we start to see other kind of application, which are interesting, for example, for Airbus, that now what you have here is a picture of what used to be the inside the KUKA Aerospace website, when you see this big robot, 2 tons, and you need a 2 tons robot actually to hold the 250 kilogram end effector. And in order to move this 2 tons robot, you need a civil engineering in order to move it. So you end up with an extremely big system where they are oversized in order to be rigid. But at the end effector is so complex, is so heavy that you start to have a compliancy over all the system, and then you need adaptation to the system. And actually, most of the use case that they have, they handle plenty of robots. And when you start to put plenty of robots together, you end up at having several limbs together. And this is exactly the kind of problems that we are trying to solve in legged robotics and in humanoid robotics. So being able to adapt to a known situation and being able to handle all these constraints together is something which is of some interest to the aerospace industry. So of course, humanoid robot is still challenging. I think this is why Boston Dynamics is not selling the robot. Actually, I asked them to buy one. It was, I think, last year in June to Herbert, and he told me, no, sorry, we can't. I think we know that it's extremely expensive, it's dangerous, you can break the robot, and having this kind of robot being support is very expensive. This is why this is not interesting for them. So humanoid robot is still challenging, and it brings a lot of scientific challenge, but which are plenty of nice application to then other robots. And I think quadruped robots, and if you look at the latest industrial robot from Boston Dynamics, basically they use all the control tools that they developed for Atlas is inside those robots, and they are super stable. They can control one specific point while moving all the other parts of the robot, while taking into account a lot of constraints. So I think there is an interesting pragmatic proof of concept. So what I try to describe very quickly is a development that we have done to the H2020 European project called Memory of Motion, and coordinated by Nicolas Mansart, a very bright colleague of my group. And we had 3 study cases one with humanoid robots in Airbus cases, the other one with the exoskeleton with Wondercraft, and the others with quadruped for inspection. And I think you have probably seen all the nice work of Maurice Fallon, our colleagues from Edinburgh, which are also a member of the Memory of Motion project. So I will not talk about this. I will focus on this first study case. And our aim was to develop generical methodology in order to generate complex motion for robots with legs and arms, focusing on reactivity in real time. So our goal for us was to consider a very simple setup display here, where you have staircases, narrow passage, uneven terrain, and see if our humanoid robot is able to generate motion in real time in this complex environment. So, of course, it's a bit hard to not talk about reinforcement learning. So I think the goal for the reinforcement learning community is to have just one big neural network computing everything, perception, and then sending automatically a goal. And there is some kind of advance, but it's still difficult to do that. And the difficulty is that actually, if you start to look at the structure of the neural networks, which I think is the biggest problem, you really need to be super careful. For example, in computer vision, starting with the ImageNet network, the training, if you can take weeks, if you don't have the proper computational power, if you don't carefully minimize the good cost function. What I think is fairly now in the community that in low dimensional space, typically 6, you will see very nice application, even in legged robotics and even in humanoid biped robotics. I think the nice talk from Jonathan Hurst and Patrick Vensing is really showing, and I think also the previous talk of Claudius Emily, that it's working. But when you start to have more complex dynamics, things are becoming a bit more complicated, and specifically with such kind of robot like TALOS, where you have heavy arms. Then you need to take into account the inertia on the leaves, and when you start to have complex environment with the geometry, then the underlying geometry of your accent space, the policy that you want to find, is becoming really complex. So what we have tried to do is to take the best of both worlds, and I think this is more or less what our colleagues are doing. So very often, and I think it was what was presented before, that you use a very good controller based on optimization, where you know it's working, when you can prove that it's working, that you're taking into the constraints, and you're trying to use reinforcement learning techniques actually to drive this kind of controllers. So here we have the classical approach, where you have a state estimator with a very quick loop, with a whole body controller, with a stabilization, taking into account a central dynamics system with low dimension to handle balance. And we know that this is needed in order to have our robot evolving in a balanced way. And you have motion planner here giving constraints and contact foothold. And then you have this flow, which is working pretty well. The only problem is when one fails, going back is very costly, and usually it's very difficult. Here, what we have been showing is that if you early on take into account careful into consideration some of the constraints, you can really break down the complexity. And for example, for contacts, when you do manipulation, you can very easily actually plan controllers. So here you have the TALOS robot looking at one box, and what he has been doing in less than 2 minutes is finding a sequence of controller where actually you are doing visual control, and everything is embedded inside the robot. And we have all this set of constraints where the robot switch from one to the other. And this is not found by weeks, days, 2 minutes, okay, of classical motion planning approach. So our goal now is to start from this kind of motion planning. And actually, the weakness of this kind of approach is that they are always trying to solve the problem from scratch at each time. But these kind of things can be used actually to drive and help your machine learning system. And actually, we apply this into industrial application for deburring, so into industrial application, and it was accepted to CAS 2021. So what we are interested in here is that, as I told you, this main problem with this approach is the fact that here in the centroidal dynamics model predictive control in the center, you are assuming the dynamics of the center of mass. Okay, and what's the main problem with robots such as TALOS is that you need to take into account the inertia of the legs, and actually the difference can be up to 5 centimeters between what will give you a classical linear inverted pendulum and the whole body motion that is executed by the robot. In order to, so if you're able to cope with that in an instantaneous way with the stabilization, you can have, if you're in flat floor, using classical techniques, you can use localization and based on the leader. So we modify the TALOS robot with a Oster 64. Here, actually, it's a work in collaboration with the team of Maurice Fallon from Oxford in the ICRA2021 robot. And in such kind of situation, now you can generate online the footstep for the robot to join some of the points which are given here. And the map, which is, so here we're doing only localization, and the map is given to the system. We have a precision of 2 centimeters using ICP and using here the visual odometry. So this work has been done by Thibaut Laguin, one of my PhD students, in collaboration with Oxford, who provided all the localization system. And here we are using the whole body motion provided by PAL Robotics. So this is the kind of stuff that you can do with a human and robot that you can buy to PAL Robotics. So I think it's kind of nice. So to come back to the problem that we want, in order to take into account this inertia and being able to improve the performance of the system or doing more complex motion, what we would like to do is to actually replace all the sequence of central dynamics, stabilization, and QP, to replace this by a whole body model predictive control. And one of the main problems that with model predictive control, that it's extremely costly in terms of computation. So again, how could we break down the complexity of solving this kind of nonlinear optimization problem? So what we have been doing is to first, thanks to the work of Steve Tonneau and Pierre Fenbach, is to use a subspace of the central dynamics and after filter it out. And it happened that if you use a specific space, you can really break down the system and plan this kind of motion on using again the torque. Here you have the TALOS robot in controlling torque. So here you have seen that the robot was not able to correctly go to the final footstep. It was still able to recover from hits thanks to the fact that it was controlled in torque. And again, this is due to the breaking down of the complexity thanks to Steve and Pierre here. So to my knowledge, I think this is the only humanoid robot that you can buy. There are other in academia which are doing also torque control, but this one you can buy it and which is able to do torque control. So the whole body model predictive control, actually to help him, and it was partly done with the system. This is one way of breaking down the complexity. The other one is to put a memory. So what we have done with Mujoko, before that we develop our own system, was to test it on HRP2. And what the main problem that we have with this kind of whole body model predictive control is that they have a large space of possible trajectory. And then what is extremely complex is to set up the initial starting point of your whole body model predictive control and the weights. So what you can do actually to help your MPC to converge toward the right basin of attraction is to build a memory of action, of possible starting state, value function, and optimal control, and actually help your robot to solve the problem. So here, this is a paper that was presented at this ICRA by Ewen Dantek. And here you have a whole body model predictive control running at 100 Hertz on a remote computer. You need a very powerful multi-threaded system actually to do that. So there are chipset now which could be put inside the system. And what is doing the person is that simply controlling the blue box, which is related to the right end effector. And here the robot has to avoid the pole in real time. And if you use just the MPC, which is a differential dynamic programming, without the memory of motion, the system is stuck. It cannot find a solution. But by exploring the state space of the system using motion planning, then you can compress the space of the initial space, and then the system is able to find and start to have a good guess of where it should start on the system. So here you won't see any multi-contact transition, which will be the next step. But as far as we know, this is one of the first time that there is a 100 Hertz MPC for the whole body, which worked inside the robot. And it's working also in torque control. And if you see the robot, even if it's perturbed, is able to reject the system. So here we have a state feedback. So there is no stabilization loop. Everything is done with the MPC. We have just one loop of the whole body model predictive control. And it's done in torque. Okay, so now that I have shown you the big picture, I will very briefly go into how we did that. So what we did first is to this is here the classical DDP formulation, where you have a cost function with a running cost and end cost. Here you have the function, and what we know is that we have thousands of variables when you consider the whole horizons, but which is sparse. So what we have done is we have done a simplistic optimal efficiency using, an optimal implementation using a simplistic one. And what we have done after is to take into account the structure of the system, and what we believe that the SQP-like approach, like I said, are not appropriate in robotics. And what works pretty much better are augmented Lagrangian to take into account the constraints using penalty-based method. And actually, what is extremely costly in model predictive control is to compute the derivative. So what we have done, we spent a lot of time craftily creating a very efficient dynamical library called Pinocchio, which is able to do a contact generation, code generation of the derivative, and which is extremely fast. And we tested into various complex systems. And using this, we implemented a multiple shooting DDP, which is able to handle the fact that sometimes you don't have a feasible solution. So the system is able to explore the space of the unfeasible solution and provide you one very efficiently. So we tried it on motion, crazy motion, like jumping with a robot, or aggressive jump. And I think here the next difficulty is that we don't take into account collision. And taking into collision is the next step. It's pretty hard. It's really making a very difficult finding the right basin of attraction. Still, if you have a robot like TALOS arm or 9-degree DOF, you can have MPC, nonlinear MPC, up to 2 kilohertz. So I think these kind of tools are really useful for the industry and more classical robotics, and could be used. So everything is open source and freely available. So what we found out is that the main point here is that we assume that we have the right model. And the problem that we have with such kind of robot is that they are very difficult to actually handle. They are very powerful, like the Atlas robot, and when you make a mistake, it can have it's super dangerous for students. So what we have been doing is looking at some of the problems that we had on the robot. Is that the fact that the torque control loop actually has a bit of a problem, that the joint torque sensor to do the torque control is outside the low-level control, and we are a bit disappointed. And it was not due to the design of PAL robotics, but some limitation of the Elmo control board. So putting this together, what we did is we introduce a new kind of robot, working together with the Max Planck Institute, thanks to Felix Grimberger and Ludovic Righetti. And we designed this kind of nice robot. Such here, you can see this is a Solo 8, which is able to jump 1 meter. So this is not the work of our team, but the work of the team of Ludovic Righetti. And well, it's super easy actually to test really quickly some control idea. And I think it was what has been shown by our colleagues on the quadrupole robot, such that we had up to 7 papers at ICRA 2021 this year using this platform. So I think this is really a success. But for us, it's going to be the next step for the future. And I think I will stop here because I'm at the end of my time. So thank you very much for your attention.
Great. Thanks a lot, Olivier. If anybody has any questions, please post it in the chat. One quick question from myself. I got a little bit confused. So in the memory of motion. So basically, the memory works in a way that you don't stack in a local minima in the MPC, right? Is this the main concept?
The point that the differential dynamic programming is a local trajectory optimizer. So basically, you have only a local optimum in the trajectory space, and if you don't start, so the whole body DDP has a so huge space that you can get very quickly easily trapped in a local minima. So what we do is with a planner, we explore the state space and learn the transition between two functions.
And how complicated moves can this be extended to? I mean, for now, we've seen just a simple, let's say, collision avoidance with a cylindrical object. But do you feel that this is the way to go to more complicated motions?
I think this is the biggest scientific question. As long as your the latent space or the space that you are taking decision is about 6 dimensions, it's tractable with almost any good machine learning techniques. When you start to go up to the other system, then you really need advanced technique, very good GPU, tiling very nicely the system, and specifically while exploring the space that you want to actually capture. I think this is very important. It's very easy actually to generate useless data sets.
All right. Okay. Cool. Any other questions? You may raise your hand if there is any. Quick question before we move to OK. I don't see any. Thanks a lot, Olivier. Again, it was very exciting. And
Thank you, Dimitri.
Let's Marco. Let's move to the next talk. Thanks a lot, Olivier.
Thank you very much, Dimitrios, for the invitation.